So today I'm going to talk about life cycle of a sample in Prometheus TSDB. I'm Ganesh Vernekar. I'm a Prometheus team member and a software engineer at Grafana Labs. Before we dive into TSDB, what is Prometheus? I hope many of you know about Prometheus here, but just to briefly talk about it, it's a metric-based monitoring system and an alerting stack. You can instrument your applications and let Prometheus scrape your metrics, and Prometheus will store them, make it available for query, alert on it, and you can dashboard things with it. So what's a time series in Prometheus? So time series has a series identifier, which is just a bunch of label value pairs, and each unique combination of label value pair identifies a time series. For example, if you change status 200 to 201, it's a completely new time series. And there is a sample itself. Sample has a unique Unix timestamp and a value. Here I take example of a float value, but this is Prometheus architecture. It has a lot of things. It has instrumentation on the left side, there is service discovery, alert manager, but at the center there is Prometheus, and Prometheus has a time series database in it. And we are just going to talk about the time series database in this talk. So time series database takes a sample where the timestamp is int64. It's a unique Unix timestamp in milliseconds. So Prometheus uses millisecond timestamps, and value was only float 64 until now, but now it has support for a complex data structure of native histograms, which is like a group of lot of integer and floats. But we will assume it's just float for this talk, and everything about the TSDB remains same, only the compression changes. So let's first look at an overview of TSDB before we dive deeper into it. So it has something called the head block. We call it head because sample first enters the head block. Head block is the in-memory part of the TSDB which handles all the data in the memory. But in just storing in memory, it takes a lot of memory. So it makes use of two things. One is RightHeadLog, which is vol, the yellow box, and there is head chunks. We will soon see what's the use of both of these things. And once we have stored the data in the in-memory head block, we convert this into persistent blocks. So when I just say block, it means the persistent block, which is the blue or the purple one here. And when I say head block, it's the in-memory thing. So let's first start with putting a sample into the head block. So zooming into the head block is, you can consider it as a simple hash map of all the time series, and each time series has a dedicated struct inside it. And that struct has all the labels associated with that time series and all the samples and chunks associated with it. A chunk here is a compressed unit of samples. For example, you have 100 samples. It is efficiently compressed into a single unit called chunk. And we use Facebook's Gorilla compression for compressing the float values. So when a sample first comes into the head, a sample I'm mentioning it as label and T1, V1, where T1 is the timestamp, V1 is the value, and labels is just the labels of the time series. So when it first comes to the head block, we don't immediately write to the chunk. It first goes into the RightHeadLog. We'll soon see why is that the case. And then we add it to the chunk. The compression is done on flight, like we don't store a buffer of samples and then compress it later. As soon as the sample comes inside the head block, we compress it and store it inside a chunk. And inside the RightHeadLog, it's called write ahead because before you add the sample into the TSDB, we want to log that a write happened. So RightHeadLog stores all the write events that happens to a TSDB. And here we say that a series was created in the TSDB. So we add something called series record. We call these records. And each series has a ID. I'm assigning it here ID1, which is a 8-byte number. And we store a samples record. And we don't want to repeat the labels in all the samples record because that would not be a good use of the disk space. And labels can be huge. So we just say ID1 has a sample T1, V1. So why do we need RightHeadLog? It's to give durability against crashes. Because the head block is an in-memory thing, like everything is in the memory. What happens if the Prometheus crashes due to out of memory error or something else? Or what if you want to upgrade your Prometheus? What happens to the in-memory data? So if Prometheus crashes, you can recreate the write events from this RightHeadLog. and recreate the in-memory structure what was there before. So let's go through the process again. So we are appending a sample T2, V2, and now RightHeadLog looks like this. We don't add a series record. We just say ID1 got another sample which was T2, V2. And we repeat the same process again, and now the chunk is full. The easiest way to proceed further is have a slice of chunks in the memory, but we don't want that. So we use something called head chunks. It's just a bunch of files on the disk. We call it head chunks because it's coming from the head block, and we just flush it to the disk and memory map it. So the OS gives you a feature called memory mapping, where in the code it looks as if it's a slice of bytes, but underneath, when you access a particular point in the slice, the OS fetches that thing from the disk and makes it available in the memory. So we make use of this feature here. So yeah, so the same process repeats. A chunk fills in, you flush it again, and you get more chunks like this. So this is a high-level view of how the in-memory database in the TSDB works. Let's go further. Now we have to create blocks out of this head block. We do this like every 2 hours in Prometheus. We'll see why we need this. So to create head block, we call this process as head compaction. Compaction is overloaded. We'll see a block compaction later on. In head compaction, we take the data of last 2 hours, like we fill the Prometheus up to 3 hours of data, and we take the oldest 2 hours of data. It can be either in the head chunks or in the in-memory chunk. We take those things and flush it into a persistent block. We'll see the insides of persistent block soon. And we just remove the data from the head and the disk files. And similarly, we get more data, we create more blocks. Okay, so far so good. So why do we need head compaction? So time series, they are not constant. Like you might have some time series right now, but later you stop giving the data into the time series. So you don't want to hold it in the memory because it takes a lot of space and it'll just go on taking more memory. So you want to remove stale series. Also the head chunks, though you flush it in the disk, you need to keep some kind of reference about that chunk in the memory. So that again takes space. So you want to clean up that regularly. So that is why we do head compaction and create persistent blocks out of it. Okay. Now what about the bigger block that you see on the side, which is purple color? It's exactly like the blocks that we see right now, but we take smaller blocks and create bigger blocks out of it. So let's take example of block A, B, C, D. Block D is the latest one. Yeah. Going back again, if you notice the numbering, I call it block N, N-1, N-2. Basically the block just gets older. The new block has a higher number. So we take the oldest, in Prometheus we group 3 blocks together at a time. We take the oldest 3 block and just replace that block. Like we merge the index and all the data of the 3 blocks, remove the old block and remove all the old blocks and replace it with the new block. This is an automatic operation. So TSDB only sees either those 3 blocks or this one block. Yeah. So why do we need to do this block compaction? It's for efficient queries. Why? We'll see soon once we see how we query these blocks in the first place. Yeah. So now that we have seen how we are storing the data everywhere, now it's time to see how we get rid of the old data, because you don't want to store the data forever. So there are 2 types of retentions that we use in Prometheus. One is time-based and one is size-based. Time-based, we will take an example of time-based here, where you say if the data goes beyond a particular time, like if the TSDB spans X hours, just remove the oldest data. And in size-based, you use just size as a metric. If the disk, you are taking some gigabytes of space, just remove the oldest data. So here the red line gives you the time boundary after which you want to delete the data. But the oldest block is already crossing that line. But we don't delete that yet because rewriting a block is an expensive operation. So we wait for the block to go entirely beyond the line. So we add some data, it creates a new block, and now the oldest block is beyond the time retention boundary. And without waiting for anything, we just delete it from the disk. It's as simple as deleting all the files of that block. Yeah. Now let's peek inside a block. So block has 4 things in it. There is the index, which lets you find everything inside a block. There is meta.json, which just stores all the metadata about the block. It's helpful when querying, like, do you want to touch this block or not? And there is Tombstones, which helps in deletions, which we'll see later, like how we make use of these tombstones. And there are chunks itself. It's chunks is a directory, and the numbers that you see 1, 2, 3 are just files. So it's just all the compressed chunks in these files. We have multiple files so that when accessing a file, you don't have to like look at a very huge file. So let's start from meta.json. It's a simple JSON with all the metadata, like each block has a unique identifier. You see what's the min time and max time that this block covers, and few stats like number of samples, series, chunks. And there is compaction. The level is just how many times this block has been compacted. And if you remember the block compaction, we took 3 blocks and created 1 block. So here it says the sources of this block was the 3 blocks that's given here, and a new block was created. Similarly, there are few more metadata information that I haven't included here. Now time to look at the chunks. Chunks is actually very simple. It's a bunch of files, and within each file, like the right side peeks you inside a single file. It's just a sequence of chunks. I'm just taking a random chunk, 30-second chunk. And if you see offset, that tells you the byte offset of that chunk. For example, if there was a 8-byte header for the file, the first chunk offset will be 8 if you start from 0th byte offset. So if you skip 8 bytes, you'll find that particular chunk. So offset 1 can be 8. Similarly, offset 2 is the byte offset from the start of the file. So when you have this offset and the file number, I give an example of chunk 34 reference. If you want a reference which can uniquely identify this chunk, you can say it's in file 2 and offset 3. And the numbers are small enough that the file number can be encoded in 4 bytes and the offset in 4 bytes. So you can use just an 8-byte number to reference a particular chunk. So we will see this offset logic in many places when we look at the block. So this is how the chunks file look like. Now there is also tombstones. Let's look at index, which is the most interesting part in this. So index has few more things besides this which are not important or deprecated. So I'm just choosing these 4 important things, which is symbol table, series, postings, and postings offset table. We'll go through each one of them. So first, symbol table. In a time series, you saw that it has label value pairs, and the label names can be repeated in multiple time series, and the label values can also be repeated in multiple time series. And you don't want to repeat this in the entire index. So what you do is you have a symbol table where you have a unique set of all the, like each string, the label name and the label value, we call it a symbol here. You have a unique list of sorted symbols here. And again, the symbol 1, symbol 2, sim 3 that I have mentioned is like an offset. So use the offset where the string is present, and that number you can use to represent a particular string in the entire index. For example, if particular place in the index says I'm using SYM3, like sim3 as my symbol, you can come to this table or just take the offset in the index and you have the string again. So this symbol is usually 4 bytes because we keep it at the start of the index. The symbol table doesn't get too huge, and you can use 4 bytes to represent any string that is there in this index. So that's the symbol table right here. Then we have the series itself. Series is again a sequence of a series basically. You store the series labels, which again uses the symbol table and doesn't store the actual string, and it is sorted with respect to the label values. And you hold a slice of the chunk references. So we saw the 8-byte chunk references in the chunks file. So we store them here, and the min time and the max time of the chunk that the chunk reference refers to. So we just store sequence of series here, and similar to the offset logic, the S1, S2, S3 are just the byte offset in the index file. Like if I just give you an 8-byte number called S2, you can directly peek into the index and get the contents of the series. Okay. Next thing is postings. postings is a term from the inverted index. Postings basically means the series IDs, the S1, S2, S3, what you saw, the series IDs, those are basically postings. And this particular part, it may not be clear right now until we look at postings offset table. It holds multiple slices of these series IDs. So there is one slice which has S3, S6, S8, S22. Similarly, we have multiple slices. It looks random now, but we'll also look at posting offset table. So PL1, PL2, PL3 is again the offsets. At the offset PL1, you have a list of some postings or some series IDs. So only PL2 and PL3. We'll come to postings offset table and see what does that actually mean. Okay, so all this is inverted index, and we'll see how to query it next. So postings offset table is like foo1 equals to bar1 is a particular label value which appears in some time series in the TSDB, and it says foo1 equals to bar1 is present in a list of time series which is identified by PL1, the posting list one. So foo1 equals to bar1 is in PL1, which means it's in the series S3, S6, S8 and S22. So you'll find this label value pair in these time series. Similarly, all the label value pairs that you see in TSDB are listed in this table. So we will see how to use this right now. Let's go through an example of a query. So when querying TSDB, you give set of matchers. So here I am taking an example of foo1 equals to bar1 and foo2 equals to bar3, which means in TSDB's term, you have to do AND operation, like the series must contain both the label values. So we have to do an intersection between both. So first we look at the postings offset table. So foo1 equals to bar1 gives us PL1 and the second one gives us PL3. Okay, so now we go on to the next step. And now we look at the postings table. And from this, we get the series IDs for the particular label value pair. Okay, nice. So now we have the series IDs for these two label values. And the next should be trivial. You just do intersection between them. And the common series is S6 and S22. So if you query, if you do this particular query, you can say that S6 and S22 has both of these label values. So what do we do next? So S6 and S22 are like direct offset of where the series is present in the index. So you directly jump into this table and get the labels and the chunk references. Okay, now you have the chunk references. You can now fetch the chunks from the chunk files. And the query usually has min time and max time specified. Like you don't want to get all the samples for the time series that you ask for. You want to bound how much data you want. So you trim the chunks here. Basically, while fetching chunks, we filter there itself, like don't fetch chunks which you don't need. But because of deletions, you want to trim chunks, which we'll see later. Yeah. So this is on a high level how querying works. This is an inverted index. So this is how inverted index query works. What about querying multiple blocks? So I consider head as a block because all of them implement the same interface for querying. So we just do individual queries. Like the query that we saw right now, we just do the same process for every block because a block is an isolated thing. A block doesn't know about the other block. A block has information about all the time series that is there only within the block. There is no global index. You do individual queries to all the blocks and just merge them or concatenate. If the time ranges of the blocks are overlapping, then you have to merge the compressed chunks because the result of query is a sorted non-overlapping data. Or if it's not overlapping, you can simply just concatenate. And some series might be present in just few blocks and not all the blocks. So the result like has data from all the blocks. Okay, coming back to the place where why do we need compaction for faster queries? So number of individual queries go down. You have to do less index lookup. And when you merge or concatenate, like in this example, a 5-way merge is way more expensive than 3-way merge. So there is less index lookup and faster merge, hence efficient queries. Also, you don't want to merge block merge blocks to be a very huge block, so there are some controls to control the size of blocks. You only merge blocks up to some extent. Like this big block will get combined with 2 more big blocks to to become a much bigger block. And it's not just equal matches. You can do not equals, regex equals, and regex not equals query on TSDB. You just look at the posting of offset table, go through the label values, and you can just apply this logic. At the end, you just need posting list for all the label values that match and just intersect them. Yeah. Finally, we look at the tombstones, the last part in the block. So when the deletion request comes to the TSDB, we don't immediately delete the data from the disk, because rewriting a block is expensive, because once you delete the data, you have to recalculate the index. So what we do is we use tombstones. In tombstones, we just like RightHeadLog, we just record the deletions that happen. Like when the deletion request comes for these labels, just delete the data in between T1 and T2. We go through the index, find out which series does this effect, and just record it in the tombstones. For example, S1, just these time ranges are deleted, and for example, S4 and S9. So it just mentions the time ranges that have been deleted for these series. And in the querying where I had the step of trim chunks, you just take care of removing those time ranges from the result for this particular series. So tombstones helps in filtering the data. Like if you have deleted a data, just don't show it in the query. And there is a operation called clean tombstones in TSDB, which will let you force delete the data, because sometimes you really want to delete the data and not just hide it from the queries. So there is that support as well. Yeah, there are a few more things. Like we saw how to add the data, how to get rid of the data from the block, but what we haven't seen is how to get rid of data from the RightHeadLog and the head chunks. So, and how to replay the data to restore the in-memory structure. So we are going to see how to replay the data from these two things and how to do maintenance on them, which is basically just removing the old data. But at the same time, I intentionally left out another thing, which is snapshots that we do on shutdown. It's an experimental feature. Not you can say you can run the TSDB without it, but we'll also briefly look at what's the use of this snapshot. So let's first look at replay that you do on startup. So the RightHeadLog basically has all the data, like all the samples that you can use to replay the data in the memory. But the head chunks already has the compressed samples, and recompressing the samples again is an expensive operation. So first you replay all the head chunks and make a map of it in the memory, like the reference and which series it belongs to. And after that, you replay the RightHeadLog. When you are replaying the RightHeadLog one by one in sequence, the series records tells you which series to create. Once you create the series, just look at this map of chunks and attach it to it. And the samples in the RightHeadLog just help you recreate the chunk that was in the memory. So the chunks that were on the disk are replayed from the head chunks, and the one in the memory you just replayed from the RightHeadLog. So this is how the replay works on startup, and that's how you restore the data in the head block. So before looking into snapshots, let's look at how do we do wall maintenance. So wall is a set of files again. It has numbers 0, 1, 2, 3, etc. And each file contains multiple records, series, samples. It also has tombstones records, but we skip it in this example. So we'll go through an example of how maintenance is done. There are many things to keep in mind. So let's say RightHeadLog has 3 files right now, 35, 36, and 37. The blue boxes are the series records, and the green ones are the samples. And to keep it simple, I have kept the samples associated with the series right after the series record. So the first 3 are like label 11, like ID 11, then 12, then 13, then 14. So we do something called checkpointing. In checkpointing, we choose the oldest 2/3 of the RightHeadLog. After we do the head compaction, we do this checkpointing. We choose the oldest 2/3, and we say that we want to truncate everything for timestamp less than 45, because let's say the head was compacted up to time at the 45. we say we want to truncate everything that was in this before 45. So I have highlighted the red boxes, the samples that are under 45. So we just remove them. After removing, you see that the series 12 doesn't have any sample at all anywhere. So we remove that record. But again, I have highlighted two more boxes, one in file 36, where within the checkpoint, like within 35 and 36, there are no samples for label 13, but it has a sample in the file 37. So in that case, we have to still keep the series record. And similarly, like in file 37, there is a sample with timestamp 30, like the first number is timestamp, second is value, which is less than 45, but it's not part of the checkpointing. So we don't remove the samples from there, like we don't touch those files at all. So now that these operations are done, we club those two files 35 and 36 into a checkpoint. You can consider checkpoint is a RightHeadLog inside a RightHeadLog. Checkpoint is a directory again which has a file 0. If there were more records, there will be a file 1. And it gets the number 36 because it says, okay, this is the latest checkpoint with number 36. So after this, you have to start replaying the RightHeadLog files from number 37. In case, like, you have to take care of all the failures that can happen with the disk. In case you were not able to delete the files due to some reason, this checkpoint will tell you have to start from the file 37. So this is how the maintenance of wall happens. And when you are replaying, you start with the checkpoint, replay as if it's a RightHeadLog, then continue with the RightHeadLog files. And when you are doing the next checkpoint, along with the RightHeadLog files, you include the checkpoint itself in the checkpointing, like you look at all those things. Yeah. Now we look at the head chunks maintenance. It is pretty simple. It is very similar to the chunks files that we saw in the block, except the headers for the chunks are a little different. The chunk reference is again same. The file number is the first 4 bytes and then the offset. So file number and the byte offset together tells you the reference of the chunk. And the head block stores all these references that it's actively looking at right now. So after every 2 hours when we do head compaction and remove the data, looking at the head chunk references in the head block, like it's not an expensive operation, you have to go through every series again. You can see which is the oldest file that is still being touched by the head block. And that gives you the number, like let's say head block has all the references which is touching files 3 and above. In that case, you can just delete the files 1 and 2. So that's how the maintenance happens. You have what's the oldest file still being used. Yeah. Now this is the last thing. We'll briefly look at how snapshot on shutdown works. In this case, snapshot is not a snapshot of the entire data. We just take snapshot of the in-memory data. So basically the in-memory chunk that is in the head block and all the series labels. And we do it only during shutdown. The whole purpose of this is to make restarts faster. And how is that? We saw that we use head chunks to replay the chunks that have been already flushed into the disk, and we use RightHeadLog to get the series and to recreate the in-memory chunk. So going through each and every record of RightHeadLog and uncompressing, decoding them is an expensive operation. At the same time, using the individual samples to recompress into a chunk is an expensive operation. But we skip RightHeadLog entirely and create just replay the snapshot which already has the series that are relevant and has the compressed chunk. So this can actually make your startup time more than 50% faster. Yeah. So the entire talk was just a movie. These are the novels. I have written a 7-part blog post in detail to talk about the TSDB. More will be coming soon, but if you are interested in knowing more in depth about the TSDB, you could go over these. Yeah, and thank you.